Hi, everybody. I thought I would do a quick video showing two examples of sample selection bias. And as usual, I'll do these examples through a graphical analysis. So we'll imagine that we have some true relationship. We'll imagine what the pattern of observations might be. We'll imagine what the threshold rule or the selection rule might be. And then we'll see what observations would actually be observed in a sample that's gone through a filtering process that's based on the outcome variable. And then we'll see, based on that filtering process, the sample that we actually observe will produce a biased estimate of the relationship. So let's go ahead and do these two examples. So the first one we'll do is we'll imagine we have a professional sports league, and we imagine we order we have junior players who are drafted into the league, and they're ordered according to their draft pick. We're going to order them so that higher draft pick means a better player. So usually it's the reverse. The draft pick number one is the better player, but we'll just reverse that origin. So we could think of it as just 100 minus the order of the draft pick. So player one now becomes player 99. So the higher the draft pick, we'll imagine, is the better the player. And then here we'll have their performance in, 2 years later, 3 years later in the NBA. So we normally would expect there'd be some true relationship. We imagine this true relationship given by the solid blue line, that the higher your draft pick, that is, the more the scouts have determined you're a really good player, probably the better player you actually are in the pros. So it isn't just random that the scouts and the algorithms that predict your likely future success in the pros are reasonably accurate, and that people who are picked for the draft earlier than others indeed do perform better. And then we'll imagine that the pattern of observations is such that there's considerable heteroscedasticity. That is, people who are sort of low priority draft picks, who are, picked later in the draft. Remember, we're ordering it. These people out here are the best players. So the best players exhibit very little variation around the predicted likely outcome, whereas the worst players who are drafted, they're still really good players, but they exhibit considerable variation. So the range of variation is large for them. The range for variation of people who are better players as we move along here, the range of variation gets smaller and smaller. So that might be our pattern of error. So this is heteroscedasticity. Notice that even though it's heteroscedasticity, the expected, sorry, I have my fading pen here. Let me change that to the regular pen. So the expected value of, the expected value of the error term, I need the eraser here. There we go. And back to the pen. The expected value of the error term, I'm drawing it as EI, conditional on the X, I is equal to 0. That is, in all cases for different levels of draft pick, there's just as many dots above as below, as many dots above as below, as many dots above as below, as many dots above and below, as many dots above and below. So the expected value of the errors for any given level of draft pick, for this level of draft pick, there's some errors above, there's some errors below. On average, they're equal to 0. So that's our condition for the estimated coefficient to be unbiased. And that's what we would observe if we had all this data. The problem is that we don't see all this data. Instead, we imagine that there's some threshold rule where players who are drafted but then perform really poorly, that is, all of these players, they get cut from the teams, and so they're no longer observed. We don't see them in any sample of data of NBA or NFL or NBA, whatever the Major League Baseball Association is. We don't observe them in performance because they all get cut from the team because they end up performing badly. So the players that we do observe who were low draft pick are the players that ended up having high performance for some other reason. They had some undiscovered attribute that meant that they performed sort of above average relative to the draft pick, whereas the people who performed below average relative to their low draft pick, they all just got cut from the team. So what does this mean for our estimation? Well, let me do a different color. Since we've cut these and we don't observe them, um, the people at the bottom of the draft pick distribution, the players at the bottom, disproportionately have positive errors. So they're disproportionately positive here. So our best fit line is more likely to go like that. We're just going to try and fit these observations that are sort of above the true line. And so our estimated line, so this would be our estimated line, that will be biased, and it'll be biased to be flatter. It will look like draft pick doesn't have such a big effect, a predictive effect on performance, but that would be wrong. And the reason it's wrong is because our sample has been selected on the basis of performance, and our sample, through the process of teams cutting players, has dropped the players who have negative errors, who are at the low end of the draft pick resolution. So the sample is selected based on their performance, based on the player's performance. So that leads to classic sample selection bias, and we would underestimate then the slope of this relationship between draft pick and performance. So that's one. So let's take a look at another example now. Now let me clear off everything here. And I think, yeah, here I forgot that I had actually drawn this. So we have the threshold and we have those cuts. And so then we have the estimated line will be flatter than our true line. Our true line is beta 1 hat is this blue line, and our estimated biased beta 1 hat is this red beta 1 hat flatter, because we don't observe these observations. Okay, let's now go to our second case. Our second case is where we have we imagine we have hedge funds or mutual funds or shares that are issued to the public in companies, and we're measuring the return on these shares over some time period, 1 year, 2 years, 10-year return. And on the x-axis, we're measuring some measure of the riskiness of these hedge funds or these companies. They might be in a risky industry, or they might deliberately leave themselves exposed to downside risk. So in finance, we often talk about risk and return and the trade-off between the two. So now we'll imagine that there's a true, on average, sort of population relationship, which is this positive line, the solid blue line that we have here, that the higher the risk, the higher the return on average across many funds or many financial instruments. And let's imagine that we have observations, and these are our observations without sample selection. And we'll imagine that very low risk funds or financial instruments have little variation. So we see some variation. Some are positive, some are negative, some are positive, some are negative. But the riskier we get, the more variation we see around the average return. We see some very extreme positive values, but we also see high negative values. So it's still the case. Let me switch to the non-fading. It's still the case that on average, the expected error, I'll use epsilon now, the expected error conditional on riskiness, which is our x variable. So the expected error conditional on riskiness is equal to 0, because some are positive, some are negative for any given level of riskiness. But we can observe now that if we have some threshold rule that says that funds that are performing very poorly close, then all the funds that are maybe below this threshold or below this threshold, all of these funds are closed, and so we don't observe them anymore in our sample. They wouldn't be in our sample because they all closed. They weren't observed for 3 years. So that's the sample selection process, and it's determined by the fund performance. So now what happens? Well, those funds go out of business. the ones that we observe below the threshold. So this one, this one, this one, this one, we don't observe them. They're not in our sample. All these are not in the sample anymore. So the ones we observe in our sample that are high riskiness are only the ones that had high returns, not the ones that had negative returns. So now what happens, our estimated line is going to be steeper than our imagined true line. So our estimated line will be steeper, and we'll have a biased estimate of beta 1 hat. So again, the sample selection results in a biased estimate of beta 1 hat. Hope you found this useful, and I'll try and do some more examples for you a bit later.